In this video, we will talk about scraping data from web pages. So more specifically, scraping data from HTML sources. So this complements the discussion of getting data via APIs as JSON or XML files. The only difference is that HTML as a data format is geared towards presentation, not data representation. So there is more effort involved in understanding how the data is presented, and this sometimes requires us to kind of reverse engineer what's inside the HTML page in order to understand how the data is structured. So in this example, we will be scraping data about the UGA football record from this web page. And once we have the data, we can answer questions such as, what's the first team that UGA played against, or what are the most challenging opponents? So let's take a look at this page. And this page, we see that we have a web page, and the data is presented in one big table in this web page. Of course, HTML is not a data interchange format, and there are many other things that we don't care about, such as the header of the page, some of the headlines, many other things that we don't care about. We really care about this data table here. So the first thing we need to do is to basically grab the page itself. So we're going to use the requests library, and we're going to send get request and grab the HTML page at that URL here. So we're going to copy the URL, and let's call response. We'll get that URL here. Hopefully we get a 200 status code, which is the case, which basically means that the page should be in the response.text here, which is basically the HTML code of that web page. Obviously, as a fully fledged page, there are so many things here, including some JavaScript, some CSS for styling the page, as well as the HTML code here. So we can see that we've got the data table here, but it's very difficult to tease out the structure of the data by just eyeballing it in the Jupyter notebook. So instead, what I'm going to do, I'm going to go to the web browser and look at the source of the web page in the browser. Now I'm using Chrome because I like the developer tools that the Chrome browser provides, but all browsers provide similar tools. If we click on inspect here, this opens up the developer web page, the developer tools page. And this gives us different extra capabilities in order to understand the structure of this page. The first tab here, elements, this is basically providing us the HTML. That's the HTML source, but it's presenting it in the document object model. Basically, we see that the browser is showing us how it's parsed the page, right? And if we hover over any element here, it's going to show us that element highlighted in the page to the side. Or vice versa, if we go to the page here, if we click on this little select element tool and we select an element here, it's going to navigate to that web page, to that HTML code and show us the corresponding HTML code. So for instance, if I select this here, it's going to go to that HTML tag, tr. So we're basically within that table, and that's a row, and this is the first column, td. And we've got different, we got the values here. Okay, so what are we going to do with this? We're going to try to parse this page. Now we can try to parse it using elementary. The only difficulty with elementary is that elementary expect a well-formed XML, and some HTML code is formatted complies with the XML format. And we can know that if we see doctype XHTML. This page doesn't show XHTML, it shows HTML. So there is a chance that this is not well formatted XML. We can try that, but most likely we will get an error at some point. So elementary is more suitable to you to parse XML code. HTML, because it kind of tolerates some degree of sloppiness, is better parsed with other libraries such as BeautifulSoup here. So what we're going to do here, we're going to create a parser to parse the HTML by creating an object from the BeautifulSoup library here. So we do BeautifulSoup and we get that object here. So BeautifulSoup provides different parsers, including a parser for HTML. So what we can do here, we can call the function, I believe it was parse. One of the functions to parse the data we have. So we probably need to pass in the object here response.text and HTML as parameter to that object here, to that constructor here, okay? So that's basically, we'll create an instance of BeautifulSoup, and this instance will parse this text using the HTML parser. So what do we get with that? Well, very similar to element 3, we've got functions like FindAll or ITER, which will basically give us the capacity to look for a certain tag or a certain path within the document. Okay, so we can look at the documentation of FindAll, for instance, and it will give us basically all of the tag objects that match a given criteria. So this is very similar to FindAll in elementary. We can also look at, I believe, ITER. I think it's all in FindAll. So, I mean, there are a couple of them, and we will be using FindAll here. Of course, we can parse the HTML document from its root, but in this case, we're looking for a specific kind of information. So what are we looking for? Well, so let's get back to the browser here. If we highlight, I mean, we are interested in grabbing this data, for instance. This one, this one, this one, this one, and this one. So you can see that all of these data elements are in the TD tags within the TR tag. So the HTML presents a table as a sequence of rows, and each row is a sequence of columns. The first row, if we need a header column, is called to be TH, which stands for table header. But all of the subsequent rows, we have TR, which is the row, and all of the columns here are the TD. The data itself is the text associated with the TD. So what we need to do, we need to grab all of the text within the TD in our from the HTML document. So if we do soup.find all TD, this will basically give us all of the TD tags here, and we can grab the text from these tags. So we can do something like tag.text for tag in soup here, and we get the data here. We can do something like that. The only problem here is that then we need to be careful when we parse it to understand when the row ends and the next row begins. This is not a big problem here because we know all rows have 1, 2, 3, 4, 5, 6, 7 columns. The problem though, if you scroll down through this table, we notice here that one of the rows here contains one column, and this is basically like an extra explanation of the row before. But from an HTML perspective, if you click on this, it's a row that has one TD, which is basically the description. Okay, so if we assume that each row contains 7 columns, and we do 7, 7, 7, we're going at some point to misalign our data, and we will have issues, because when we hit this row that contains explanation, we're going to bundle it as the first column in the next row, like this one. So you'll get the next 7 as here, and then the next 7 will be this one, and then we will have issues. So in order to kind of resolve this problem, I'm going to select rows instead of the columns, and then I'm going to call a function to extract the columns from the rows. And once we do that, we can, within this function, test whether we have 7 columns within the row. Otherwise, we can return like not available or none to indicate that this row is not valid. So let's take a look at the first row. Oh, let's take a look at the, not the first, the second, because the first is the header, right? And this one contains 7 column here, okay? So I'm going to do rows here equal to soup.findAll tr. And then what I'm going to do, I'm going to create a function called Parser. So what I'm going to do, I'm going here to do columns, is to do row.findAll td. Let's see if this is working for me. The rationale here is that columns is a tag, row is a tag, so we can, like an element, and we can call FindAll on it. So if I do parse row, rows1, it's actually td, not rd, we get the 7 columns here. So here I can be more specific, and I can say that if length of columns is not 7, less or more, I'm expecting 7 here because I got 7 columns here. 1, 2, 3, 4, 5, 6, 7. If this is the case, I'm going to print cannot parse row plus row. Let's convert it to a string here. Again, that's an object here. It's an element object. And I'm going to return none. Else, we can do our regular kind of operation. We can do process these 7 columns. So what am I going to do with them? Let's return. I'm going to return a dictionary here. I can return a series, but let's return a dictionary mapping the column header to the column data. So here we have these things, opponent, first game, so on and so forth. So what I'm going to do with this, I'm going to associate these with their values. So the opponent will be column0.text. The first game will be columns1.text, right? So it's 0, 1. And last game will be columns2.text. G, which is the game number of games, will be columns3.text. Columns4.text. Loose will be columns 5. And finally, the tie would be column 6 dot text. Now there's an opportunity here to convert these data to integers. It's possible to post-process it as well. So we can do this. Since those are numbers, we can convert these to numbers. Int. Not so sure about first game and last year, although year is strictly speaking a number. We don't really care about its numerical properties, so I'm gonna leave it as text. Okay, so what do we get here? We get a Python dictionary, and we've got here the keys and the values. All right, so very nice. Now we can do this on all of the rows that we've got. So obviously there are different ways to do it. One way to do it is to use Python, so we can use a built-in list comprehension, so we can parse row of row for row in rows. And this will basically give us a list of things. Of course, those are the error messages, and we've got an issue with the first header row, which is to be expected. Because we don't have TD, we have TH, so that's 0, and then we've got those 2 extra rows that have explanations. So we've got a couple of nuns here. So we can store this as data here. And then what do we do with this data? We can create actually a data frame from it. So we can do data frame data and from data. The only problem here is that because we've got none, pandas did not understand to treat dictionaries as columns, because some of these entries are not dictionaries. So we can filter the data. We can do D for D in data if D is not none. And without the none, pandas will understand that since all of these dictionaries have the same keys, it makes sense to make them columns, and we've got ourselves a nice data frame that we can save and refer to. So that's one way to do it. The other way to do it is to do the conversion load the rows themselves in a series or in a data frame. So like we can do pd.series rows. This will basically be a series of these rows. And then we can do apply parse row here. And then we can do drop NA because we've got 2 nuns. And then we can do a data frame from this series. From this series itself. Probably need to get the values because otherwise it's just using the row values. Okay, let's see what's going on here. We lost the dictionaries for some reason. Interesting. So I'm not sure what's going on here. It's possible to make that conversion, but since we have it here in DF, let's proceed and try to use this data frame to answer the questions. So 2 questions here. What's the first team that UGA played against? So then let's sort values first game. And we can see here that, well, so UGA played their first game in 1892, and their two teams played against in 1892. So of course, the first one that comes in this can be accessed with ilog 0, 0. The problem here is that we've got two teams, right? Mercer, and the second team was Auburn. So ilog 0 doesn't get the right answer because there are two teams. So what I'm going to do to get the value of the first here, which will be obtained by ilog 0, 1, or 0, comma 1 here, right? 0, 1, that's the first game. Or we can do ilog 0 and then first game, which is slightly more verbose here, right? So that's our first tier. And then what we can do, we can mask based on the first tier, or we can set the index. So if we don't want to do a mask, we can do df first game is equal to first tier, right? And that's our df here, df, and we can pull opponent here. And of course, if we wish, we can convert this to a list. Well, the other way to do it is, instead of using masking, we can do df set index to be first game. Changing the index allows us to do lock on the index at lock first tier. Okay, and the remaining thing is the same. We pull opponent from this data frame, and then of course we can convert to list if we wish. The second question is asking us about the most challenging opponents. And this is kind of an open-ended question, like how do we know whether the opponent is challenging? Of course, we can look at the percentage of lose against that opponent, right? So like if you look at Alabama, for instance, UGA played 69 games and lost 40, so obviously this is a very challenging opponent, okay? Compared, for instance, to Alabama Presbyterian, with which UGA played 2 games and won 2 games. So the problem here is that this doesn't take into account the number of games played, because, like, you know, if you take a team like, let's see if we can find an example here. Let's do sort values on L. I'm looking for like a team with which UGA played once and lost. So this team will be very challenging, but we only have 1 game, which is not a lot of observations to extrapolate from. So that's it. Seems like UGA played so many games and didn't lose against. Very good, go dogs. So let's crunch the numbers and we'll see what I kind of mean by that. So what I'm going here, I'm going to create a new column. Let's call it challenging 1. And challenging 1 will be the percentage of games lost to that team. So an easy one to do it is to do dfl divided over dfg. Okay, so that's the percentage of the games lost against this team. And then we can do sort values challenging 1, child 1. I'm going to do ascending false, and let's do the head here. So that's what I meant, like a team like Cumberland, UGA played against once and lost, which makes it very challenging, but that doesn't take into consideration the number of games played against that team. So again, this really depends on the criteria that we are creating for determining whether this is a challenging or not. I mean, it's not a very well specified problem. We can do another criteria. We can say like, how about we do challenging 2 as DFL instead of dividing it, and do that. This is just counting basically. Of course, I could have probably sorted by L because there is no transformation here anyhow. This makes Auburn the most challenging teams because UGA lost 54 games against this team. So that's another way to do it, but I mean, again, this doesn't take into consideration the percentage of loss. Maybe because UGA plays Auburn a lot, it lost 43% of the times, but against Florida, it lost 44% of the times. Against Alabama 57%. So what's the criteria here? We can think about another way to change it. So we can do, how about challenging 3? I'm going to divide losing over winning, right? And then this makes like we're looking at a percentage of losing against winning, and then we can weigh this by the number of games played. So again, it's kind of like I'm playing with the data to kind of come up with a meaningful scenario here. This was not very meaningful here because we've got these small teams again. So we've got infinity because this one is 0. So what I'm going to do DFL plus DF winning. So what I'm trying to do, I'm trying to look at the percentage of losing compared to losing and winning. So I ignore all ties, but I want to kind of normalize this by the number of games. So I've got a similar rank to the previous rank: Auburn, Florida, Alabama, Georgia Tech. So again, there's no right or wrong answer here. It depends on how we kind of trying to kind of use our own judgment and provide some face validity to the measurement, which is not provided for us. We provided a very kind of high-level description, and we're trying to come with a meaningful measurement of what challenging means. Of course, that depends on our domain knowledge as well as our common sense here. But if you look at this kind of header data frame, the name of the teams here makes sense. We can all recognize these teams as challenging teams that UGA played against. The key point of this exercise, not kind of to derail, is not data analysis per se, is basically reading from HTML. So before I close in, I'm just going to show some nice features of BeautifulSoup. We can find all based on a tag, but we can also combine. If you look at the documentation for FindAll, you can see that you can also provide an extra dictionary of the attributes. And this provides us a way to look at a certain tag with certain attributes. So for instance, if you're looking at an attribute like, let's go here to, for instance, column span. Anyway, would you look at column span here? That's kind of an attribute. You can look at FindAll TD. And then call span. That's the attribute. And then the value here is 7. And we get the match with that attribute, right? So that's the column that spans 7 columns. That's the the explanation column. And we managed to nail it down because we know that this particular column has a column span of 7. So this is nice because this is kind of like an XPath. It is allowing us to match on both the tag and the attributes of the tag. But of course, if you look at the documentation of this method, you can also match on the text as well. So it's providing similar kind of matching capabilities to XPath. Um, and we can combine different tags, different attributes, and different text to get to different parts of the HTML document. All right, that wraps up the discussion here. Again, to summarize, BeautifulSoup is a library that allows us to parse HTML. It also has a capability of parsing XML, HTML documents, and it's much more powerful than Elementary, and it kind of tolerates different issues and sloppiness in HTML documents. The key function here is FindAll that takes a tag and give us a list of elements representing these tags, and then we can access their text, their attributes, their children, very much like what we have done with Elementary. So we use it to get all rows, and then for each row we got the columns. And once we get this data, we kind of pass it along to pandas. We get our data frame and we process the data in the data frame. All right.